All right, hello everyone. This is going to be the tutorial on I'm all the way at the bottom because I was doing this earlier, on Unit 4, Lesson 5, about Earth having different regional climates. Like there's a nice, pretty picture of the Sierra Nevada mountains. That's like close to where we live. These are called Indian paintbrush flowers. It's not very culturally appropriate anymore, I guess, but that's what they're called. All right, so it starts off with, throughout the whole lesson, it talks about why do these regions in California have such different climates, and it uses Yosemite National Park and Joshua Tree National Park. These are both parks in California, both extremely popular. And so it says, why do you think the short-term and long-term weather conditions are different in different locations of the world? So these clearly are both in California, but they both look very different. And why can they have such different climates? And so what I said was because weather is affected by wind currents and geographic features like mountains, how close they are to the ocean, winds coming off of the ocean, and things like that. These, depending on where a place is, right, if there are mountains or no mountains, or if it's by the ocean or if it's not by the ocean, that would obviously affect what the climate is like. And identify differences between the parks and list your observations. So some things that I said were, of course, there's no right answer to this. You're making observations. But, here in Yosemite, it's very green. There's lots of greenery, lots of large trees. I didn't even notice this before, but there's actually a deer right over here eating. There's clearly water. So you've got that going on. And there's these huge mountains in the background. This is actually this right here, I know, is in particular photo is in the valley. So Yosemite is a large park, but it's famous for the valley where there's large granite rocks to either side. And then in Joshua Tree, it's pretty dead. There's not a lot of green. Really, the only green is on the edges of these trees. These are called Joshua trees, which is where the park gets its name. These trees are only, I think, around this area in Southern California and around, I believe, in Israel, I think. And they're a type of yucca plant, which is kind of like they're related to, oh my gosh, cactuses. They're like a type of, they're not really cactuses, but they're close to a cactus. If you've ever seen one up close, they're really pokey, and the end needles are more like spines, like a cactus, like you'd see on a cactus. So I'm going over exploration 1 and 2 in this. So describing climate. So climate is the description of the average weather over an area over a long period of time. And so a lot of times you'll hear things like, why did, a lot of times you heard people talking about like global warming, and then everyone started calling it climate change. Why was that? And one of the reasons was because there was a misconception when people would talk about global warming that it means everything's going to be hotter. And that's not really what it means. The entire Earth was getting hotter, but that doesn't mean that the climate everywhere is going to get hotter. Some places it actually might be colder. And so people started referring to it as climate change because what it means is that the climate or the weather in certain areas over long periods of time would change. And so it gives you different examples of different types of climates. And this says, are there popular sports where we live due to the climate? And I said there's pretty much everything because we live in a really unique area, being right between mountains and the ocean, and also being kind of at a latitude or in an area of the world where we have cold winters and hot summers that we get a really wide range of sports. Whereas, maybe if you were in Hawaii, you wouldn't have snow and things like that. So maybe you'd be primarily like surfing or beach type sports. Or if you lived in, Alaska, it might be more towards the winter sports. But we actually get kind of a nice combo of both. Down here, it has a graph of San Francisco and the average temperature. It says this graph shows San Francisco's climate over a 1 years. Oh wait, no, that was wrong. These averages were calculated over a long period of time, from 81 to 2010. This is 30 years. Oops. 30 years. I didn't notice that at first. Probably because I didn't read the description. I think I read over here. So see, it says that these are calculated over a long period of time. So this is climate versus weather. Weather would be like a year. The warmest month is September. So you can see how these are color-coded a bit. This dotted line is the temperature, and the precipitation is the bars. So September is the highest temperature right here. And the rainiest month is January. So when you look at the bars, which is the precipitation, January is the highest, most inches or millimeters of water. And this talks about describing climates. Usually the focus on climates is talking about temperature and precipitation, because those are things that can really easily be measured over long periods of time. So here's a graph that talks about the climate of Beijing, China. And it says, circle the names of the months with temperatures at or above 20 degrees. So 20 degrees is right here. And, oh, you know what? I missed. Oh, my word. I was looking at precipitation when I did this one. So it's actually, let me get a circle here. Fixing my own stuff. I highlighted them at first, but it should be May through September should be circled. You got, let me delete these other ones, because I was flip-flopping I was looking at the bars, not the lines. But again, the bar is temperature, and these precipitation is the bars going up is the precipitation, and the line graph part is the temperature. And this was talking about temperatures. Temperatures 20 degrees or above. And that is 20 degrees is right here. So that would be May, June, July, August, and September. Of the months you circled, which month has the least amount of precipitation? So I need to change this. And it looks like from here to May has the lowest, right? The bar graph in May is lowest. So May is the least precipitation. And it doesn't specify whether the precipitation is snow or rain. I'll probably have to change this answer as well, because I used the wrong graph. So it says, use the graph to infer which months the rain would be. So when I'm looking at the temperatures, right, the temperature is, this is 32 degrees right here. So it looks like, so if the temperature was under 0 degrees Celsius or under 32 degrees, it would definitely be freezing, because that's colder than freezing. So in January, February, and December would be less than 0 degrees Celsius, so it would likely be snowing. Other months are over freezing, so it would likely be rain. Okay, moving on. Exploration 2. This talk tells us to think about how the ground would feel on our bare feet. And I said, and it asks, will they have the same temperatures? Why or why not? And I said they definitely don't have the same temperatures, and I do think that the type of surface has an effect. An example was like on a hot day. I'm sure we've all walked outside on the grass on a hot day and probably don't notice much. But I'm sure many of us have walked on a beach during the summer, and the beach sand can feel a little bit hot at first. And I think probably most of us have definitely walked out onto the street barefoot at some point in time in our lives during the summer and quickly realized that we should not be standing there because it's very hot. So it looks like the surfaces, definitely do make an effect. And this talks about how the Earth is absorbing a light as radiation, and how some of it's absorbed by some of it is reflected by the atmosphere, some of it's absorbed by the atmosphere, but a lot of it gets absorbed by the surface. Now, this we skipped. Number 9, I said to skip. But this is talking about sunlight and latitude and how sunlight affects latitude. Now, latitude is how far north or south you are from the equator. So here's the equator, right? Latitude would be measuring like how far up or how far down you are. Now, the point of this experiment was you can kind of see it right here. Now, you have this flashlight, and if the flashlight is pointing directly down, it would make a circle. Now, if you angle the flashlight, right, it's going to make more of an oval shape. But actually, this oval is taking up, if you were to do this yourself and try and figure out what the area of these circles and these ovals were, even though these flashlights, right, the idea is that these flashlights are the same distance away from the paper, and they're both putting out the same exact amount of sunlight, but the one that's more direct, right, has less area, and this one that has more at an angle has more area. Well, how does that affect the Earth? So you can see the same concept is happening here. The sun is equally, it's 93 million miles away, so it's equally as far essentially, no matter where you're at on Earth. And so the sunlight coming to Earth has the same amount of energy. But if you're near the equator, all this energy is being focused in a really tiny area. In comparison, then the light coming up towards higher latitudes is more spread out over the same area. So because the same amount of energy, like the light has a certain amount of energy, but that light energy is getting spread out over a larger area. So it's actually not getting as much energy from the sun if you're at higher latitudes because the light is spread out versus the latitudes near the equator. So the idea is that, as you get further away from the equator, the sunlight is actually transferring less energy to the surface, which is part of the reason why, it's one of the big reasons why the poles are colder and the equator is warmer. Another thing that affects it is called the albedo. And the albedo describes how much sunlight a surface reflects. And so the moon doesn't have much to do with Earth. It's just kind of as a comparison. But you can see how this shows the sunlight coming down, and it's showing us approximately how much of the sunlight is being reflected. So you can see fresh snow has a really high albedo. 80 or 95% of the light that's coming from the sun is just reflected right back in fresh snow. And this is why if you've ever been to the snow, a lot of times you can feel like you're getting sunburned if you don't wear sunscreen or something like that. Or if you've ever seen pictures of mountaineers, a lot of times their faces are really dry and sunburned because they're closer, they're at really high elevations, and then the sun is just reflecting all that light right back into them. It reflects a lot of the light. And then you can see how forests and crops and grass, you can kind of do a comparison. But the important thing is these dark roofs and asphalt blacktop, this is reflecting 5 to 10%. It's not reflecting a lot of light. Which means it's absorbing the vast majority of the energy from the sun. So whereas snow bounces a lot of that light energy back, asphalt absorbs it all. So when humans build a parking lot of dark asphalt on top of the grassy field, the albedo of the surface decreases, right? It went from, let's say, 20 or 25% to 5 or 10%. And when ice and snow melts due to changes in the climate, the soil and the rocks are revealed, and the albedo also decreases. So it's saying, if you go from snow and the snow melts and then you have rocks left, rocks are going to be like concrete or asphalt. They're dark, or like a dark roof. It's darker. At most, it's going to be like a light grass or something like that. So you can see how anytime snow melts and reveals what's under it, the albedo will be decreasing because it's not going to reflect as much light. And this is how might the surface types in Yosemite and Joshua Tree National Parks affect their climates. So one thing I said was, going back to the picture of Joshua Tree and Yosemite, there is a lot of open area here, and it's brown. And when brown can be considered to maybe be a darker color, there's not a lot of shade for the ground to cool off. And it's pretty much going to have the same albedo year round. Now, Yosemite, on the other hand, has lots of different types of terrain. It's got rocks, it's got sand, it has water that's going to reflect a lot, like you see in that picture below. It's got trees and forests. And a lot of time throughout the year, Yosemite is actually, much of it is frozen. If you've ever visited Yosemite during the winter time, the vast majority of the park is completely closed down because it's completely covered in snow. So those would definitely affect it because it's obviously not snowing in Joshua Tree, so it's going to be absorbing a lot of sunlight year round. Whereas in Yosemite, when it snows, it's going to be reflecting a lot of that energy, half the year. Then we have analyze rooftop and albedos in Los Angeles. It has this nice little chart where it shows the colors, right, of the rooftops, and that represents the percent of sunlight that's being reflected. So the more blue it is, the more sunlight is being reflected. So the red, orange, and yellow roofs reflect 0 to 25% of sunlight. These roofs are likely to be warmer than the green and blue roofs, and that's because the green and blue means that it's reflecting more light. So a lot of that light energy from the sun is being reflected back, whereas these darker roofs, which are the red and the orange roofs, they're absorbing a lot of that energy. And this is saying what's likely true about the air temperature near all of these roofs. And the air temperature would be slightly warmer near those roofs. And that can be really easily be seen if you're sitting under a tree or in the grass on a hot summer day. It doesn't, it can seem a little bit cooler than if you were standing in the middle of an enormous parking lot. If you're sitting in the parking lot, you're surrounded by lots of dark pavement, and in the hot metal cars are absorbing all this light, and it's heating the air up around you, versus the grass. And this says you're part of a planning group that wants to make the air temperatures in this part of Los Angeles cooler. Write a recommendation, and basically my recommendation is don't build roofs out of dark colored materials and make them as light as possible, because if they're darker, it's going to attract more light, it's going to get warmer, it's going to heat the air up. And if they're light colored, then it's going to reflect most of that. So that is all for today, and stay tuned for exploration 3 and 4.